Following the baseline methods, the team successfully implemented a genetic algorithm to develop a machine learning pipeline. A genetic algorithm starts by generating random permutations, which are also known as species. And for our project, these permutations consist of combinations of pre-processing and classification pipelines from sklearn. At each iteration, each pipeline is trained on the dataset. Depending on which of the pipelines score the best, certain pipelines are duplicated with parameters adjusted slightly for the next generation. The lowest scoring pipelines are discarded so that the total amount of pipelines remains unchanged. More sophisticated algorithms also incorporate a crossover rate where the compatible features of certain pipelines are mixed for the next generation. With the assistance of a library called Teapot, the team implemented a genetic algorithm to optimize a machine learning pipeline. Teapot is built on top of the scikit-learn library, and a list of some of the preprocessors and classifiers that are iterated through are shown here. The XGBoost classifier was also added by creating a wrapper function that calls training and evaluation subroutines and defines the parameters in the same style as scikit-learn. The settings we used are shown as well. One drawback of using a genetic algorithm is the amount of time needed to run each generation. We ended up using just 10% of the dataset, and the algorithm was run overnight to maximize the number of permutations exercised. The best performing algorithm was developed with the genetic pipeline, The best performing algorithm that was developed with the genetic pipeline outperformed all the baseline pipelines and achieved a log loss score of 0.54. This pipeline happened to be the same XGBoost library that was tested earlier, and this score was roughly equivalent to a top 20% in the Kaggle contest. Interestingly, the best preprocessor appeared to be no preprocessing at all. We believe this is because the classifier uses far more boosting estimators, so finding the best features occurs more naturally and the heterogeneous data is less of an issue. Now, these results are promising since they match what many participants in the Kaggle contest found to be the most efficient algorithm. But they're also slightly disappointing since they don't necessarily say anything we don't already know, which is that support vector machines and gradient boosting tend to work well on just about anything. So in order to find something more interesting, the team improved the Teapot technique based on some of the ideas we discovered earlier, specifically stacking. One thing the Teapot architecture can't do is look at stacking methods. However, when the algorithm runs, the methods it trains end up being thrown away in favor of algorithms that are slightly more accurate. So instead of effectively wasting these already trained algorithms, the team attempted to reuse them in combination with the original algorithm selection to create an automated stacking pipeline. The Teapot automated approach was modified so that the final 4 best algorithms were combined to form a single stacking classifier. The types of the 4 classifiers were kept distinct, and under these circumstances, the pipeline received a score of 0.519, which was one of the most